Okay. So as promised, we are doing trapezoidal sums this time to help us estimate the area under the curve. As we've seen with integrating these, just integrating these integrals, we're having a hard time finding things that work nicely, right? If there was even an extra variable somewhere, things wouldn't work out. We've gotten a way to get most of our integrals done with U substitutions, having the antiderivatives of those inverse trig functions in our book now, exponential, and the natural log being an antiderivative. But there's still so many things that we can't actually integrate. So again, that's where these sums come into play, so long as they're continuous. I don't know why it's labeled 7.8. Couldn't tell you why. Well, I guess I could tell you why it's called numerical integration, but I think the name of this would be better to call it trapezoidal sum. That's an argument for another day. I will read what I have written here, and then we'll get into how the formula works. So I have numerical integration is the process of approximating a definite integral using well-chosen sums of functions multiplied by their integral widths. So technically, a Riemann sum is numerical integration, right? We are going to do something similar to Riemann sums. Riemann sums use what shape?
Rectangles.
Rectangles. And we're just going to be using trapezoids, which just this shape. Parallelogram, and I'm just going to make one of the edges flat. Can you guys look up the area formula for a trapezoid, please? Yeah. I want you guys to still look it up so that you have the visual in front of you as well. So yes, 1/2 parentheses base 1 plus base 2 times height. What's base 1? Sure. Just one of them. So then the bottom one's base 2. And then the height, that. So I'm going to take this and rotate it so that the flat part of it is the x-axis portion. And maybe I'll just use this trapezoid here. So then our height becomes what?
Is what? The base.
Yeah, kind of the base. And how would we calculate that? Yeah, x2 minus x1. And then I don't care, again, you could put b1 or b2 on either side. It doesn't matter. You're just using those two heights. Now, how would we find the length of base 1 or the length of base 2? Lydia?
Would be from wherever f(x1) is in this case.
Yeah. Yeah, base 2 in this case would be f of x1. I should probably switch the labels. Not like it matters. So let's say that we have some random interval that we want to find the area for. We would find all of those little trapezoidal areas, add them together, and that would approximate the area underneath the curve, right? I'm going to use the summation notation and I'll kind of walk us through it. So it'll be the sum from I equals 0 to n minus 1, and we'll talk about why in a moment. And it will be 1/2. Whoops. 1/2 base 1 plus base 2, but in this case, we use the function values to get those. So it'll be f of x I plus f of x I plus 1. So left endpoint of the interval plus the right endpoint of the interval, their outputs. Oh, I'm running out of room here. And then how did you guys say we find the width again? Or the base?
That's G minus X.
Yep, x2 minus x1. In this case, it'll be those two x values that we have here subtracted. So xi plus 1 minus xi. Now, because this could get pretty lengthy, I'm going to suggest when you guys are doing these, maybe get the width, this part of it, the change in x values. Maybe calculate that and not write the subtraction, because that could end up being a lot of extra writing on your paper on top of what's already going to look like a lot of writing. Question. Okay. The next thing I want to talk about is how we determine if a trapezoidal sum is going to be an overestimate or an underestimate. So what I would like you to do is look at each of the sections where it's an overestimate and see what they all have in common. So go ahead and do that for me. There's some obvious overestimates and then there's some not so obvious overestimates. Go ahead and look at that. And if you want to discuss with the people around you, go ahead and do so. Can I have a show of hands? How many people think that they know the relationship? Yeah, Gavin, go ahead. That's exciting.
It's gonna be an overestimate if it is concave.
I have a pretty obvious like concave up there, right? And yeah, let's see. That's an overestimate. That's concave up there and here. Nice. So I'm assuming the other relationship concave down is under. Perfect. Thank you. I'm actually going to write under here and over just so I have that visual. But we'll write that information in our table. I do have a little extra space so we can talk about like the derivative and second derivative values. So over, that was concave up. And how do we know if a function is concave up?
The second derivative.
And the first derivative would be increasing. Concave down, exact opposite information. Okay, so we have our first example. I have 3 of them. One where I give you the graph and you can draw in the trapezoids if you so choose. One where we're doing this from a table, and then one where we're doing it from a function. So you have access to visualizing how to do all of the work for those 3 different things. So here it says approximate the integral from 0 to 2.5 of f of x dx using a trapezoidal sum with 5 subintervals of equal length. When they're equal length, you can go ahead and do that calculation for delta x. When it doesn't say equal lengths, you aren't going to do that. They could be all different lengths. So what is the length going to be? How do I calculate that?
Just take the 0 to the end of the interval and then divide by 5.
Okay, so the length of that interval is 2.5 and divide that by 5 subintervals, you said?
Yep.
And we should get 0.5, which hopefully it was obvious by the number of coordinates in the graph and the number of tick marks that we were going to get 5 sections. So let's go ahead and draw our trapezoids in there. And it's okay if you don't want to draw the trapezoids. So I'll start off with the first two trapezoids with you guys, and then you can finish that calculation. I personally like to rewrite my integral up every time because technically we are approximating it. So I like to write that approximately equal symbol. You don't have to. If you just want to do the calculation of the trapezoidal sum, that is a-okay. So first trapezoid, what's the calculation for that area?
Would be 0.5. Times 1/2.
I'll do 1/2 first.
Okay.
So 1/2 times, I'll do 0.5 for that.
1.37.
Yep. So 1/2 times the width of the bottom, or that delta x, then times those two heights, the function values. I'll do one more with you guys. Anyone else want to tell me the calculation for the next one?
1/2 times 0.5. And then 2 plus 1.65.
Keep going. You guys can get the rest of those, and I'll just put the work up on the board.
Could you just factor out 1/2 and 5 just add together?
Yes, absolutely. And I was hoping that you guys would see that as you were doing your calculations. You can absolutely factor out that 1/2. In fact, I would recommend doing that on any of these problems because you're always going to have the 1/2. And then if those widths are equal to each other, you can go ahead and factor that out. So maybe I'll redo the work with that. And when you guys are done, you can look up and see how it looks. What do you get?
3.2.
Okay, I heard 3.59.
3.59.
How many people got that? Because that's also what I got. Okay. So clearly things could easily go wrong while you're typing things in, right? Yeah. So if you did not get that, I will take a look at it with you. You might be missing a decimal. I might not catch it for like 5 minutes after staring at it. Little tiny things could possibly be entered in wrong. What can we do to kind of see if we're at least close to what this is? Even though 3.2 is actually still pretty close, I would say. But if we were to get, I don't know, something like 1, how could I double check to see if I'm at least roughly in the right ballpark with maybe a different problem?
I mean, like the whole graph from the 0.2 on the y-axis to the 0.25 on the x-axis, you can calculate that like a rectangle. And
Yeah.
that's 5. And it looks like the graph is covering like roughly 3 out of 5. Or 3.9.
Yeah, so you could do like, are you saying like that?
Yeah.
Yeah, you could do an overestimate and then maybe you also calculate the area with like the lowest value and try to see what that gets you, like a ballpark range for the areas. I like that. Now that also kind of makes me think like you could just try to figure out what the middle Y value is within all this and see maybe what that area is, just to get a few different ideas for where do I want this area to potentially be? Does that make sense? Okay. Example 2. Using a table, and this one also asks us to determine if it's an overestimate or an underestimate. Can you guys tell me what information I will need later on to be able to do that?
Just to get my concave up.
See if it's concave up or concave down by looking at the slopes of the secant lines. Teamwork. So right now, I'm just gonna straight up make sure that I have enough room for later. And we're calculating, or we're approximating the derivative by looking at the slopes of the secant lines. All right, just like last time, I'll go ahead and do the first two intervals with you guys, the first two trapezoidal areas. Now, are all the widths the same this time? So we have to have those calculations separate. You can still factor out that 1/2 if you like. It'll be completely up to you guys. How many people would like to factor out that 1/2 that's in every area? Okay, cool. All right, factoring out that 1/2. What do I need to calculate the first area? Other than the 1/2. 4 minus 1 to get the width, right? So that would be 3. And then what am I multiplying that by?
7 plus 2.
Yep, the heights of the endpoints. Do you guys think that's enough to kind of help you get through the rest of those areas? Okay, go ahead and do that. And when you're done, get your calculation for me and then compare your work. And when you finish that calculation, you can go ahead and start calculating the slopes of those secant lines. Remember, change in y over change in x. You even wrote it. All right, so it looks like you guys have values for at least the trapezoidal sum. What are you guys getting? Yeah. And I'm kind of curious if we could do that same strategy from the front, considering it's just like the table from the graph. I think for this, we would get a crazy overestimate and a crazy underestimate though. So what do you guys think that the middle y value would be? If you had to choose between 7, 2, -1, 3, and 5, what do you think the middle value would be between all of that? Yeah, maybe 3. And then the width of this? What's the width of the entire graph that we're looking at here? Not 10, 9. So let's take 9 and multiply it by what we think the middle y value would be, which is 3, to get like a roughly rectangular area. And yeah, we get 27. At least it's in the 20s. Considering we don't have a nice shape of the graph and we literally just have coordinates, I think that's okay. How many people have the secant line slopes? Few of you? All right, I'll give you guys about another minute to calculate those. They don't take too long. All right, what are we getting for the slopes? So 1.67 or -1.67? I want to do decimals just so it's easier for me to compare.
-1.5. -1.75.
Is that what you guys were getting? Or 3?
Oh, I did 1.
Okay, yeah, I think that's what I got as well, 1.3. And then 2. All right, so what's going on here? Yeah, you look at every single slope, it's definitely consistently increasing. So what does that tell me? Yep. So just to make sure that we have the proper wording, since the slopes of the secant lines, or delta f over delta x, which represents roughly what? The derivative. Since that is increasing. This implies, and I don't care if your wording is a little bit different, so long as it logically like flows from one part of your statement to the other. That you said it's concave up? Okay, and I'll also put that F double prime is greater than 0. Oh, over what interval? Because it's not always,
Over 1 to 10.
yes, not including the endpoints. We don't know for sure there. Those could be points of inflection. So what is our conclusion about this trapezoidal sum?
1.5 is an overestimate.
Overestimate, yeah. Therefore, this trapezoidal sum is an overestimate. All the buzzwords that we need are in here. And I'm going to box the words that I would be looking for when I'm grading your papers. I definitely want to see like you figuring out that this is increasing, but the major things that I'm looking for to get most of the points is that you're saying that it's concave up and that it's an overestimate. That those things answer the entire question for sure. Any questions? All right. Last problem, and probably the most annoying because it's a composite function, which means not so fun stuff happening in the calculator. I'm going to write it kind of the longer way, and I'm going to suggest you guys take a look and then maybe do it the shorter way when you do it on a practice. So in this one, we are asked to approximate the integral from 1 to 3 of sine of ln of x dx. What mode should we be in considering we have a trig function? Radians. Make sure you do that right now. So we're going to approximate that using a trapezoidal sum with 6 subintervals of equal length. Ding, 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 equal length. Let's figure out the width. How do I do that again?
Your right endpoint minus your left endpoint divided by however many intervals you need.
All right, so basically the width of the entire interval divided by 6. 2 over 6 is 1/3. Okay. And if you're the type of person that needs to drop a number line starting at 1, adding 1/3 to each thing, go for it. There's no shame in needing that visual cue. All right, good so far? So I'm going to factor out the 1/2 from all of those area calculations. And because all of the widths are the same, I'm going to factor out the 1/3 as well. That way I can just focus on the heights. Now, have you guys noticed that all of the heights in the middle get used twice?
Yes.
But the heights at the very, very, very ends of the interval, like at 1 and 3, yeah, are only once. Because I'm gonna have to type sine of ln of x with the number into my calculator so many times, I'm gonna multiply those middle heights by 2 instead of writing them up twice. You guys cool with that? Okay. So what would this look like? Anyone want to give it a go?
You start off with f(1).
F of 1, which would be sine of ln of 1.
Yeah.
Oh, and your calculator is going to put a parenthesis after that ln, so maybe we should match what the calculator is going to do. Again, like I said, obnoxious. So that's the very, very first height. Then all the other heights before we get to the end are gonna be used twice. One with each trapezoid on either side of it, right?
So plus 2 sine. Of 1 and 1.
1 and 1/3, or 4/3. So 2 times sine of ln of 4/3. What I like to do is just literally add 1/3 to each of those x values. And then you can simplify as you go if you want. So like the next one, that would be 2 sine of ln of 5/3. You can keep going. Just remember, when you get to that endpoint of 3, you're not multiplying it by 2 because that's not being shared with another trapezoid, and that you have to stop at 3. So go ahead and keep doing that. And I think the easier way to do this is maybe just to know what those values are, like what sine of ln of 1 is, and maybe write that instead, so you don't have to type in sine of ln of 1 plus 2 and sine of ln of 4/3. Does that make sense? Okay, so go ahead and continue writing, and I'll let you figure out what kind of strategy you want to use to type that in the calculator. Because my dumb self decided to type the entire thing that I wrote on the paper into my calculator. And I did not trust my answer. Six thirds is 2. Seven thirds. 8/3, and then the next is 9/3. That reduces to 3, so we do not use that twice because that's the very end. Just to kind of make sure that we have all the information that we need here, you should end up getting 1.14 roughly. And then, good way to double check. Type that integral into your calculator. See if you're getting something similar to that. The trouble is with this stuff though, is that you're probably not going to get a number that's too far off. But hopefully it's within like a few decimals. Oh, forgot to multiply, easy fix. I do want to take a look at the graph though, just to see if it's an over or an underestimate. So sine of ln of x. And I don't want to look at everything. I'm going to look from, let's see, 1 to 3. And then what are the possible outputs for sine?
Anywhere from, oh, just 1.
Negative 1 to 1. So do we have an over or underestimate and why?
Underestimate is concave line.
Perfect. That's all you have to say. And make sure, well, I guess it's not all. Make sure you say the interval open.